third part of the series on functions. In this video, we'll be looking at a type of functions known as quadratic functions. Quadratic functions are functions that are closely related to quadratic equations. Let us take a look at a quadratic function. F of x equals 2x squared plus 4x minus 5. Well, a quadratic equation and standard form for this would be 2x squared plus 4x minus 5 equal to 0. Essentially, when you're solving a quadratic equation, you are telling that y value is 0. In a function, the output we get is the y value as x is the input. So when in a quadratic equation you're saying equal to 0, you're saying what are the values that are present when y equal to 0. That is basically what are the x-intercepts, because y equal to 0 is basically the x-axis. Throughout this line, the value of y is 0. So they're asking you the points of the graph which intercept the x-axis. A quadratic function allows us to use many values. You can input any x values and find out the coordinating y value for that. A quadratic function always produces something called a parabola when it is graphed. You might be wondering, what is a parabola? Let us graph a quadratic equation to understand that. F of x equals 2x squared minus 4x minus 5. This is a parabola. A parabola is basically a U-shaped structure, you can say. But in mathematical terms, we can describe a parabola as a symmetrical plane curve which is roughly U-shaped. Over here, there is something very important we need to look at. And that was the symmetry part I told you. I said it's a symmetrical plane curve. Symmetry means on either side of a line or a point, something is the same. It's like a mirror line. You have a mirror, you're standing here. On the other side, it will look the same. So when about a point or a line, something looks dissimilar, that it's symmetrical. Suppose you have a square like this. We can have a line of symmetry over here, and that can be line at the middle. On both the sides, the diagram looks the same. Or you can have a vertical line of symmetry, and then you'll have both the sides similar. So a line of symmetry is nothing but a line that divides this structure into two equal halves or two identical halves. Now, let us try to find the line of symmetry of a parabola. In all parabolas, the point at which both the curved lines meet. When I'm talking about curved lines, I'm talking about these two lines. The point at which they meet is known as the vertex. This point. This is known as the vertex. This point, a line drawn upon this point would be the line of symmetry. Suppose we draw a line about this point, that is like this maybe. This would be the line of symmetry. You see, on both the sides it looks the same. Now let's find out why quadratic functions are in the form of a parabola. Let's take the function 2x squared plus 2. F of x equals 2x squared plus 2. Let's construct a graph for this function on our own instead of putting in the function itself. To do this, let's take f of 0, f of 1, f of 2, f of minus 1, and f of minus 2. f of 0, so 0 squared into 2, 0 plus 2, so that would give you 2. F of 2, f of 1, that would be 1 into 2 plus 3, 1 into 2 plus 2, that's 3, and then f of 2 will give us 10. F of minus 1 will give us minus 4. Actually, this over here won't be 2, this will be 3. No, this will be 2 and this will be 4. And then minus 2 will give us minus 10. These are the values that we have. So if we plot this on the graph, our points will be over here 0, 2, 1, 4, 2, 10, minus 1, minus 4, and minus 2, minus 10. These are our 5 coordinates. So first we're going to have 0, 2, 1, 4, 2, 10, that's here, 2, 10, and then now we have the other side, which is minus 1, minus 4, minus 1, minus 2, 10, minus 2, 10. Those are our values. If we connect all of these lines, you'll probably say this doesn't look like a parabola. Yes, it doesn't. But if you plot in all the possible values, you will get a parabola. Think about this. How many numbers do you think are between 0 and 1? There are infinite numbers between 0 and 1. You can divide 0 and 1 into many equals. So, when we add in more and more detail, instead of just directly jumping from 0 to 1 or 0 to minus 1, the graph will become more and more curved, allowing us to form this U shape. Let us test this out. Let's take f of 0.5. F of 0.5 and f of minus 0.5. F of 0.5 gives us 2.5 and f of minus 0.5 gives us minus 2.5. Let us get rid of these lines and then add these points and draw a new line and see how that looks. So we have 0.5 comma 2.5, that would be right here, and then we have minus 0.5 comma minus 2.5, minus 0.5 comma 2.5. Yeah, it won't be minus because both of them are going upwards. So what a mistake. Okay, now if we connect these points, you notice that the graph is more curved than the previous one, which looks somewhat like this. It looks somewhat like this, while this one looks somewhat like this. This has more, not able to draw it properly, but let's just say this has, you can see it over here, this has more of a curve than a straight line. this goes like this, while the previous one went like this. So as we add in more and more values, this straight line will slowly become like this, allowing the shape to form, which is why we have parabolas. The increase is not linear. It doesn't increase by 2 or a 3 every time. But on both the sides of the line of symmetry, which is the y-axis in this case, both of them grow in a similar pattern and not in a linear fashion, which allows for a parabola to form. A parabola doesn't always open upwards. A parabola can open downwards too. By that, I mean, if you look at this parabola, you can see that, uh, yeah, you can see that it's continuously opening upwards. It just keeps growing upwards. But a parabola can grow downwards too. Let us take another function to see that. That will be f of x equals minus 2x squared plus 2x plus 3. This is a concave down parabola. A parabola which is shaped like this are known as concave parabolas, concave up. And a parabola shaped like this one are known as concave down parabolas. These are the two types of parabolas that are considered as a function. I don't know if you noticed, but there is an evident pattern over here. Over here, if we go back to the whiteboard, our initial function is 2x squared plus 4x minus 5, f of x. This is the one that gave us concave up parabola. Our concave down parabola was minus 2, it was minus 2x squared plus 2x plus 3. And this gave us a concave down parabola. There is a pattern over here. If you noticed, the value of a for a concave up parabola is 2, and for a concave down it's minus 2. All concave up parabolas have have a as a positive integer, and all concave down parabolas have the value of a as a negative integer. If the value of a is positive, you can say that the parabola is going to open upwards. But if the parabola has a negative integer, then it's going to open downwards. Now let's try and find the domain and range of a few parabolas. Our first one, f of x equals minus 2x squared plus 2x plus 3. We need to find the domain and we need to find the range. So let's not try to find it on our own. Let's just go to a graph, plot this out and see what it gives us. Minus 2x squared plus 2x plus 3. We already have this over here. Now this graph, what do you think will be its domain? We know the domain values are x and range values are y. So what are the possible x values we can have? Let me zoom out so that you get a better idea. Do you think the parabola is going to end at a point? The x values keep growing and the y values keep growing. It doesn't. A parabola has an infinite number of x values. all x values can be in a parabola. All possible x values, all integers, all real numbers. So our domain will be x belongs to R, real numbers. What about our range? Our range is a y values, which is the straight line, all these values. If you notice, you can't have a y value of 8, a 6, a 4. This is the maximum y value we can have. And this would be the y coordinate of the vertex. The y coordinate of the vertex is the maximum y value you can have in a concave down parabola. Remember, it's for a concave down parabola. The y coordinate of the vertex is the maximum y value. So, if we find out the vertex, let's just say it is, yeah, it's right here. It's at 0.5, 0.5 comma 3.5. So the y coordinate is 3.5. The y value has to be either lower or equal to 3.5. It can't go higher than 3.5. So range for this case will be y lower than or equal to 3.5. Let's take a look at another function, and that is f of x equals 2x squared plus 2. Now let's plot this and look at the graph we get. This gives us a concave up parabola, and again this parabola also goes on forever, which means it keeps getting wider and wider as you go up. If you notice, it's more wide at this point than this point, which means it covers all possible x values again. So our domain for this one is also going to be x belongs to R, and when it comes to the range, it will be over here. If you notice, we have a concave up parabola, not a concave down parabola. In this case, the y coordinate of the vertex is a minimum value we can have. For a concave down, the y coordinate of the vertex is the maximum y value, while for a concave up, it is a minimum y value. So, a range will be y greater than or equal to the y coordinate of the vertex. We'll find that would just be 0 comma 2. 0 comma 2. So y greater than or equal to 2. It cannot go lower than 2 because you see that the graph is not over here. It's not present anywhere here. It's present only, it's moving upwards. So 2 is the minimum y value. Y greater than or equal to minus 2. Let us take a look at one last function, and that is f of x equals to 5x squared plus 3x plus 11. Our domain, at this point you should know that our domain is always going to be x belongs to real numbers, because it doesn't matter if the parabola is concave up or concave down, it covers all the x values. So any domain for any parabola, any quadratic function, would be x belongs to R. Now when it comes to the range, We need to plot this graph again because range is not that easy to find. 5x squared plus 3x plus 11. We plot this parabola. We have it here. We know the domain, so we need to find the range. It's a concave up parabola, so the y-coordinate of the vertex will be the minimum value. So our vertex would be at this point 10.55. So y greater than or equal to 10.55 is our range. Vy greater than or equal to 10.55. From these three functions, we can conclude two things about the domain and range of quadratic functions. The domain will always be x belongs to real numbers, and when it comes to the range of the parabola's concave up, the y value of the vertex will be minimum, and if it's concave down, the y value of the vertex will be maximum. Now let's take a look at a different parabola. Suppose you have a parabola that looks like this, or even like this for that matter. Do you think this parabola is a quadratic function? There are two ways to check it. If you remember, in the first part of the series, we discussed what are the different types of relationships that a function can have. Do you think one value in a domain can map to two values in the range? No, it can't. This type of relationship is known as a one-to-many relationship, and this relationship cannot be in a function. If we take the domain as x and the range as y, then we can see that at any one given x value, there are two y values on the graph. Suppose here you have the x-axis and you have a y value of 2.5. You have two x values, two y values for this one point, which means one is to many, one-to-many relationship. And this relationship is not accepted, right? So it's not considered a function. A test that is usually done to test if something is a function or not is known as the vertical line test. If you draw a vertical line through any parabola, if it passes through more than one point, then the parabola is not a function. It's not just for a parabola. You have any diagram. Suppose you have a function that graphs like this. If we draw a straight line through this, there are so many points through which the line passes through, which means this is not a function. Suppose you have a concave up parabola. If you draw a straight line at any given point, it only passes through one point. And that's the same case with a concave down parabola. At any given point, the line passes through one point in the graph, which is why they are functions. Concave up and concave down parabolas are quadratic functions, while concave right and concave left parabolas are not functions at all. This is all for this video. In the next video, we'll be looking at the different ways to present a quadratic function and how to find various information using that. Thank you so much for watching. Subscribe to our channel, like the video and comment down your thoughts and